Okay, everyone. In this video, we're going to talk about 4 common ways to actually choose a sample. Let's get into it. Before we start, let's quickly refresh the basic idea of sampling. The population is the entire group we're interested in studying. Then, from that population, we choose a smaller group called a sample. That's the basic setup. The question this entire video is really about. How do I choose a sample from a population? If I choose badly, that sample may not represent the population very well. And if the sample doesn't represent the population, my conclusions could be misleading. So choosing the sample well is incredibly important. Now, the reason all 4 of these are called probability sampling methods is that chance plays a role in the selection process. Every member of the population has a known, non-zero chance of being chosen. And we'll start with simple random sampling. Okay, so let's take a look at this picture because it really captures the whole idea of simple random sampling in one image. On the left, you can see the full population. There are 30 students total. Every one of those students is a possible choice. In the middle, you see the random selection process. That's really the heart of simple random sampling. We're letting chance do the choosing. And on the right, you can see the final sample. 6 students were selected. Student 3, Student 6, Student 12, Student 19, Student 24, and Student 27. Every single student on the left had the same chance of ending up in the sample on the right. Nobody was favored or deliberately skipped. Nobody was chosen because they were easier to reach. The selection was random. Every individual in the population has an equal chance of being selected. On the next slide, we're going to look at how we actually carry this out in real life. So how do we actually do this? Step 1. Build what's called a sampling frame. That sounds technical, but it's really just a complete list of everyone in the population that we're able to reach. For example, maybe it's a spreadsheet with all 1,000 students listed. Nothing mysterious, it's just the list. Step 2. Assign each person an ID number. Student 1, Student 2, and so on, all the way through the full list. Now every student has a number, which makes the random selection process much easier. Step 3. Generate random numbers. And here's where I'll save you some unnecessary pain. You do not need to write 1,000 names on little slips of paper. Put them in a bucket and shake the whole thing around. You can use a random number generator or tools like Excel or Google Sheets. One easy method is to place a random number next to every name in the spreadsheet. Sort the spreadsheet by that random number column, and then take the first 100 students. Done. Step 4, and this part matters. Select without replacement. That simply means once someone has been selected, they stay selected. So, if student number 427 gets selected, we don't want that same student showing up again later. If we need a sample of 100 students, we want 100 different students. Now let's look at a small example so you can see exactly how it works. Let's do a small example together, so you can see simple random sampling in action. Suppose I have a class roster with 30 students, numbered from 1 through 30. And I want to choose a random sample of 6 students. So I use a random number generator, and it gives me these 6 numbers: 3, 6, 12, 19, 24, and 27. And that's it. Those 6 students become my sample. Now here's what I really want you to notice. I didn't choose the students sitting in the front row, nor choose the students who happened to walk into class first. And I didn't simply ask for volunteers. Why does that matter? Because each of those choices could introduce bias. Students who volunteer might have stronger opinions or might simply be more comfortable participating. Instead, I let chance make the decision. That's the whole point of simple random sampling. It's fair by design. Every student had the same chance of being selected, and that helps keep the sample as unbiased as possible. So when is simple random sampling a good idea? And when might it let you down? Let's look at both sides. First, when it works well. Simple random sampling is beautifully fair. Nobody is favored, and everyone has the same chance of being selected. It also works especially well when you have a complete list of the population, and when the population is fairly homogeneous. By homogeneous, I mean everyone is the same. Now let's look at the other side, where you have to be a little more careful. The big issue is this. Random does not automatically mean representative. Here's what I mean. Suppose a college has 10,000 students, and 1,000 of them belong to a special program. Now, you randomly choose a sample of 100 students. On average, you would expect about 10 students from that program. But because the selection is random, you might get only 3, or maybe you get 18. Both are possible. So if accurately representing that subgroup really matters, plain, simple random sampling can be a bit of a gamble. There's also a practical limitation. Sometimes you simply don't have a complete list of the population. So even though simple random sampling sounds great in theory, it may be impossible to carry out in practice. Okay, take a look at this picture because it shows stratified sampling really clearly. On the far left, we have our whole population. There are 40 students total. But notice that they've been divided into 4 groups: freshmen, sophomores, juniors, and seniors. There are 10 students in each group. These groups have a special name. We call them strata. Now look at the middle column. From every single stratum, we randomly select a few students. You can see the green check marks. Some freshmen are selected, some sophomores, some juniors, and some seniors. Then, on the right, we get our final sample of 12 students with every grade level represented. And here's the phrase I really want you to remember. We sample from every group. That's the heart of stratified sampling. No grade level gets completely left out. Each important subgroup has a place in the sample. And that's exactly what makes stratified sampling so useful when representation matters. Let's slow down and really understand this one, because stratified sampling is a powerful method. First, the vocabulary. A stratum is just one group. So if I divide students by grade level, all of those groups together are called the strata. With stratified sampling, we sample from every group. Now let's look at the easy version on the right. Imagine a school with 100 freshmen, 100 sophomores, 100 juniors, and 100 seniors. That gives us 400 students total. And suppose I want a sample of 40 students, because every grade level is the same size. This is pretty simple. I take 10 students from each grade. 10 times 4 gives us 40. So every grade level is represented equally, because every grade level was equal in size to begin with. But here's the part students sometimes forget. Within each stratum, the actual selection is still random. So I take the 100 freshmen and randomly choose 10 of them. Then I take the 100 sophomores and randomly choose 10 of them. Then I do the same thing for juniors and for seniors. Stratifying tells us which groups we need to sample from. But inside each group, we still use random selection. Now, real populations usually aren't this neat. The groups are often different sizes. So next, let's see what happens when the strata are unequal. Okay, this is the slide where a little bit of math comes in. So let's go through it carefully together. Here's our setup. Suppose a college has 1,000 students, but the groups are very different sizes. There are 500 first-year students, 300 second-year students, 150 third-year students and only 50 fourth-year students. And we want a sample of 100 students. Now, before we do the correct calculation, look at the trap in the red box. You might think, well, there are 4 groups, so I'll just take 25 students from each one. That sounds fair, but it actually creates a problem. The fourth-year students make up only 50 out of 1,000 students. That's just 5% of the population. But if we take 25 fourth-year students in a sample of 100, they suddenly make up 25% of our sample. That's a huge overrepresentation. And at the same time, the first-year students make up half of the population, but they would represent only 1/4 of the sample. So here's the rule. Don't split the sample evenly when the groups themselves are not evenly sized. Instead, we use the formula shown on the slide. For each group, take the size of that group, divide by the total population, and then multiply by the desired sample size. Let's walk through the table together. First-year students. 500 divided by 1,000 is 0.50. Multiply that by 100, and we get 50. So we select 50 first-year students. Next, second-year students. 300 divided by 1,000 is 0.30. Multiply by 100, and we get 30. So we select 30 second-year students. Continue on in the same manner. Now let's check our total. 50 plus 30 plus 15 plus 5 equals 100. Perfect. And here's the beautiful part. The proportions in our sample now match the proportions in the population. Then, just like before, within each group, we still choose the actual students randomly. That method is called proportional stratified sampling. A few practical notes before we wrap up stratified sampling. First, what happens when the formula gives us a decimal? We round to a whole number. The only thing you need to watch is the final total. After rounding all of your groups, make sure the numbers still add up to the sample size you wanted. Sometimes you might need to adjust one group by just one person, so everything adds up correctly. That's completely fine. Now, when does stratified sampling really shine? It works especially well when your population contains important subgroups, and you want to make sure every one of those groups is represented. Think about different divisions within a college. Now, where can stratified sampling get tricky? There are a few places. First, you need to know quite a bit about your population before you start. You need to know which people belong to which strata, and usually how large those groups are. Second, you need clear rules for people who don't fit neatly into one category. For example, what do you do with a student who has 2 majors, or a student who hasn't declared a major yet? You need to decide how those cases will be handled before you start sampling. And finally, your strata actually need to make sense for the question you're studying. If I'm studying opinions about cafeteria food, and I divide students by eye color, that probably isn't helping me very much. Blue eyes versus brown eyes probably isn't the great cafeteria divide we've been looking for. The groups should be connected in some meaningful way to what you're trying to understand. So stratified sampling is powerful, but only when the strata are chosen thoughtfully and the proportions are handled carefully. All right, let's look at the picture for our third method, systematic sampling. Instead of choosing each person separately at random, we do something a little different. We choose a random starting point and then select every kth person after that. Look at the row of 20 people. Up in the corner, you can see that our random starting point is person 3. So we begin with person 3. Then we move forward using a fixed interval. In this example, that interval is 5. So starting at 3, we add 5 and get 8. Then we add 5 again and get 13. And one more time, we get 18. So our sample is person 3, 8, 13, and 18. You can see those 4 people highlighted on the slide. The pattern is really simple. Random start, then jump by the same amount every time. It's almost like walking down a line and tapping every 5th person on the shoulder. Nice and simple. Now the next question is, how do we know what that interval should be? That's what we'll figure out on the next slide. So the one number we need for systematic sampling is the interval, and we call that interval K. The formula is right at the top of the slide. K equals the population size divided by the sample size. That's it. K simply tells us how far apart our selections should be. Let's use the example on the screen. Suppose a store expects 1,000 customers during the day, and we want to survey 100 of them. First, we calculate K. 1,000 divided by 100 equals 10. So our interval is 10. That means we'll survey roughly every 10th customer. But here's a step people sometimes skip. We do not automatically start with customer number 1. Instead, we randomly choose a starting point, somewhere between 1 and 10. Let's say our random starting point is 7. Then we simply count by tens. Customer 7, then 17, then 27, then 37, then 47, and so on. Each time we add 10, until we've selected the full sample of 100 customers. And remember, the random starting point is what gives the method its probability-based foundation. Here's a smaller example, so you can see every step clearly. Suppose there are 20 customers, and we want a sample of 4. So first we calculate K. 20 divided by 4 equals 5. That means our interval is 5. Next, we randomly choose a starting point somewhere between 1 and 5. Let's say our random start is 3. Now we just add 5 each time. Customer 3, then customer 8, then customer 13, then customer 18. That gives us 4 customers, evenly spaced, starting from a random point. Simple. Now look at the box on the right, because there's one little wrinkle. What happens if K is not a whole number? Suppose we have 1,000 people, and we want a sample of 150. 1,000 divided by 150 is about 6.67. That's not a nice, clean interval. In an introductory course like this, we can round to a practical interval, such as every 6th person or every 7th person. The exact idea that matters is this. Population size divided by sample size tells us roughly how far apart our selections should be. So don't get too stuck on the messy decimal. Focus on the method. Now, why is systematic sampling so useful? Because when people or objects already come to us in some natural sequence, this method is incredibly easy to use. Think about customers walking through a door, cans moving down an assembly line, or houses lined up along a street. You choose a random starting point, and then you count at a regular interval. Imagine a factory produces 50,000 cans in one day. Instead of generating thousands of random ID numbers, the factory might inspect every 200th can. Much simpler. But systematic sampling does have one real danger, and that danger has to do with hidden patterns in the order of the population. That's what we'll look at next. So, systematic sampling has one important trap you really need to watch for, and it's called periodicity. That's just a fancy word for a repeating pattern in the population. The danger happens when your sampling interval accidentally lines up with that pattern. Let me show you what I mean with the example on the screen. Imagine a factory has 3 machines. Products come down one conveyor belt in a repeating order. Machine A, Machine B, Machine C, then A, B, C, over and over again. Now suppose you decide to inspect every third item. Before I give you the answer, look at the pattern for a second. If you start with the first item and then select every third item, which machine do you land on every single time? Right? Machine A, every time. Look at the highlighted boxes. They're all products from Machine A. So your sample would be 100% Machine A. And you would learn absolutely nothing about machines B and C. That's a serious problem if your goal is to evaluate the quality of the entire production process. And this problem can happen outside a factory too. Imagine surveying one customer at exactly the same time every hour. You might accidentally keep reaching customers from the same employee, the same shift, or the same type of traffic pattern. The issue isn't that systematic sampling is bad. The issue is that the sampling interval can interact with a hidden repeating pattern. So before using systematic sampling, always ask yourself, is there some repeating structure in this population that could line up with my interval? If the answer is yes, be careful. Because in that situation, systematic sampling can give you a very misleading sample. Okay, our fourth and final method, cluster sampling. And this is the one students most often confuse with stratified sampling. So watch closely. This picture makes the difference really clear. On the left, our population is made up of 8 entire classrooms. Now, instead of choosing individual students from all 8 classrooms, look at what happens in the middle. We randomly choose a few whole classrooms. In this example, we select Classroom 2, Classroom 5, and Classroom 8. Then, on the right, we survey everyone inside those selected classrooms. Every student in Classroom 2, every student in Classroom 5, and every student in Classroom 8. So in this example, the classrooms are the clusters, and the students are the individual members of the population. We randomly choose some whole groups and then include everyone inside the groups we picked. Notice what happens to the classrooms we did not select. We completely leave them out. We do not take a few students from every classroom. That is the key difference. With stratified sampling, we sample from every group. With cluster sampling, we choose only some groups and then take everyone inside those selected groups. If you remember that one contrast, you'll have a much easier time keeping stratified and cluster sampling straight. Let's dig into why you would actually choose cluster sampling. Look at the classroom example on the left. Imagine a school district with 50 classrooms, with about 25 students in each classroom. And the district wants to collect student opinions about a new lunch program. Now, one option would be to create a giant list of every student in all 50 classrooms, and then randomly select individual students from that full list. But think about the logistics. You might end up needing 2 students from one classroom, 1 student from another, 3 from somewhere else, with your sample scattered all over the school. That can become a real headache to organize. So instead, we treat each classroom as a cluster. We randomly select, say, 8 of the 50 classrooms, and then survey every student in those 8 selected rooms. Much more manageable. Now look at the example on the right, because this is where cluster sampling really becomes useful. Suppose I want to survey households across a huge city. If I randomly choose individual households from all over the city, I might have to travel from one end of town to the other, then back again, then somewhere completely different. Great for your gas bill, not great for your research budget. Instead, I could divide the city into geographic blocks Then I randomly select 20 of those blocks and survey every household inside the blocks I chose. Now the data collection is concentrated in a smaller number of locations, instead of being scattered across the entire city. And that can save a huge amount of time, money, and effort. That's really the main reason researchers use cluster sampling. It makes large, geographically spread out studies much more practical. So let's be honest about the trade-offs. Because cluster sampling has one major strength and one major weakness. When your population is spread out or difficult to reach, cluster sampling can dramatically reduce travel, time, and administrative work. In fact, large national studies often use this idea in several stages. For example, researchers might randomly select some states, then some districts within those states, then some schools within those districts, and then some classrooms within those schools. That's called multi-stage sampling. And it's a very common way to make large studies practical. But now, look at the weakness on the right. And this one is important. People within the same cluster often resemble each other. Think about a single classroom. Those students share the same teacher, the same curriculum, the same schedule, and the same general environment. So if you only choose a few classrooms, those classrooms might not represent the full population very well. This problem is called within-cluster similarity, and is the main weakness of cluster sampling. Which brings us to the idea at the bottom: good clusters versus bad clusters. Ideally, each cluster should look like a small version of the whole population. So imagine a classroom with a real mix of students. Different majors, different ages, different backgrounds, different experiences. That kind of classroom can make a pretty good cluster. But now, imagine a university where one building contains mostly engineering students, and another building contains mostly art students. If you randomly choose only 2 buildings, your final sample could end up very unbalanced. So cluster sampling works best when the clusters are diverse on the inside, and each one reasonably resembles the larger population. That's the trade-off. Cluster sampling can save a huge amount of time and money, but you have to be careful that the clusters themselves aren't too similar internally. Let's bring everything together with one final example, using the same population in 4 different ways. Imagine I want to study student satisfaction at a university with 20,000 students, if I have the full student roster, and I randomly choose 500 student ID numbers. That's simple random sampling. If I divide the students into freshmen, sophomores, juniors, and seniors, and then randomly select a proportional number from every class level, that's stratified sampling. If I put all 20,000 students into an ordered list, calculate my sampling interval, choose a random starting point, and then select every 40th student. That's systematic sampling. And if the university has 800 course sections, and I randomly choose 20 of those sections, then survey every student inside the sections I selected. That's cluster sampling. Same 20,000 students, same general research question, but 4 completely different ways to build the sample. And here's the main idea I really want you to walk away with. There is no single sampling method that is always the best. The right choice depends on the situation. It depends on how your population is structured, what information you already have, how important it is to represent particular groups, how much time and money you have, and how much risk of bias you're willing to accept. Because in the end, the goal isn't simply to get a sample. The goal is to get a sample that gives you useful, honest, and reasonably representative information about the population you actually care about. And that's what good sampling is really about. Nice work, and I'll see you in the next video.